Okay, so today kicks off a two-day exploration into the topic of databases. Most specifically, we're going to look at Microsoft's flagship database product, SQL Server. And in these videos, we're going to be using two editions of SQL Server, both of which available within the Visual C# 2010 Express Edition. Namely, we're going to use the SQL Server 2008 Express Edition and then also the SQL Server Compact Edition databases. And I'm going to focus mainly on the former one, the Express Edition, because it's really just a scaled down version of the full SQL Server 2008 Professional and Enterprise editions. But near the end of tomorrow, I'm also going to look at the Compact Edition, which eventually that we're going to use whenever we start to build applications that only need to run on the client. So in other words, they don't need to access any centralized database on some remote server. If that doesn't make sense, don't worry about it. By the end of the 2 days, and especially by the end of the series that you'll be going through, you're going to have all the information you need to make some good choices about what type of version or edition of SQL Server that you really should use. So first of all, let's start as basic as possible. We're going to answer the question, what is a database? What is it? Why would you ever want to use one? How is it structured? And things like that. And then after we get some of the basics established, then I'm going to demonstrate how to create a new SQL Server 2008 Express Edition database using the Visual C# 2010 Express Edition IDE. And then I'm going to demonstrate how to modify data that you store within a SQL Server database. And so hopefully by the end of today, you'll have a pretty good overview of how databases work and how to work with them. Okay, so what is a database? Well, simply put, it's a structured repository, a structured storage area or file for your data. You save information into a database. You read information from the database. You can update information in the database, and sometimes you might even need to delete data from the database. The information is organized so that it can be retrieved easily, and it can be sorted. It can be grouped. It can be related to other data that you might have. And so you can use it to analyze information in a countless number of ways. So let's say that you have a business and you want to keep track of your customers somehow. And there's a lot of products on the market, but let's just keep this simple for the moment. You could store all your names in a simple text file using Notepad or something like that. Or you could use the techniques that we demonstrated earlier in this series using the Stream Reader and the Stream Writer. But the problem is that after a while there are so many names that it simply becomes unmanageable, both from a coding perspective if you were to try to write an application to find a particular name in that file. And then also from a performance perspective, I mean, you might get to the point where you have tens of thousands of names in a single a Notepad file or text file. You're going to have to reinvent a data storage and retrieval mechanism to accommodate new fields of information that you want to store, to accommodate the sheer number of records that you want to store. And sure, you could open up Notepad, you can use that as your user interface to find things like customer names, but you're going to have to scroll through this long file in order to find the customer that you need to follow up with, right? So you decide that storing the names in a text file isn't a good option, and you consider an Excel spreadsheet, which works for a while. But then you realize that managing a large spreadsheet could be problematic due to, again, its sheer size. But then also, what happens when you want to view all the purchases in the month of April for your top 10 customers? I suppose it's possible using Excel, but it's not easy. What happens when you need to share the data with other people in your organization? Well, you could just give them each a version of the file, right? But then who has the official version of the document that will ultimately be updated? And how do you distribute that on a daily basis through email? That's not a good solution either. How do you integrate the data in the spreadsheet with your other back-end systems like your website and your ordering system and things of that nature? Okay, so now you're just beginning to experience the tip of the iceberg in regards to the challenges around managing data. Fortunately, these tasks are well suited for a database management system like SQL Server. And up until a few years ago, SQL Server was considered a high-end database server product used in large companies to enable the management and the retrieval of relational database data. In 2005, Microsoft released an Express Edition, and now they have a second version of it called SQL Server 2008 Express Edition, where you can harness the power for the purposes of learning the basics of SQL, or you can even use it for smaller applications and smaller websites. There's just a few differences in how the Express Editions work compared to their big brothers. For example, they restrict how many users can access the database, how many computer resources can be devoted to the database itself, like how many processors and how much memory can be devoted, the total size of the database, and things of that nature. But in its most simplified form, getting back to the topic at hand, a database is simply a file on some computer hard drive that can save data in a consistent and structured way. Typically, the file structure is optimized for fast data retrieval, and it enforces certain rules, which we're going to talk about in a moment. In addition to a file, there's usually a programmatic way for inserting new data, for updating data, for defining, or I'm sorry, for deleting data and finding or selecting data. So when we use the term, and I've used it actually once or twice throughout this series, the term Relational Database Management System, or RDBMS, we're talking about a specific type of database. There are many different types of databases over the years that have been concocted. But at this point in computing history, the relational database seems to be the most popular. And what do I mean when I use the term relational database? Well, this is actually a philosophy or an approach to defining how data will be saved in a database. It's analogous in some ways to writing object-oriented code, in so much that relational database theory involves a set of rules to guide you in how to define data that would be saved and how it's related to other data within this file structure. Just to be clear, relational database theory is very different from object-oriented programming. They have different techniques, different goals, and so on. However, you can see that it's the same in so much that it's an organized approach that you'll see in both of those areas. And I just wanted to kind of associate it with something that you're already somewhat familiar with. Okay, so a little bit of background here. Relational databases were conceived in the 1970s by an IBM researcher named Codd. And they were popularized in the 80s when his theories began to find their way into commercial tools. Codd wanted to solve two basic problems that existed with databases up to that point, where all the data was handled by these large mainframe computers, and storage capacity was extremely limited and extremely expensive. He wanted to, first of all, reduce the footprint of the data, therefore reducing the amount of space that would be required on one of those big reel-to-reel footprint, reel-to-reel tapes that each database record required, which would reduce how expensive that data was to actually ultimately store. And he wanted also, secondly, to enforce data integrity. Okay, data integrity, what is that? It takes several forms. We're basically referring to the accuracy and the correctness of the data that we're actually storing. We'll talk about data integrity a little bit more in just a moment. Okay, so to accomplish both goals, Codd proposed several new ideas at that time. First of all, if you break up one long row of data fields and you organize them into several smaller structures for the data, which he called tables, and each table describing a specific subset of the data that's collected, then you could improve the integrity of the data. There's a series of steps that you can apply as you consider how to split up that data, what bucket or what table to put it in. And that process is called normalization, and we're going to devote a video to that a little bit later today. To help enforce data integrity, secondly, developers must define what type of data that they want to store, which prevents string or characters in a field that, for example, might only be allowed to store numeric values. So enforcing strong data types makes the data more correct and therefore helps to maintain the integrity of the data. Thirdly, he suggested by storing a data entity in just one place, in one record, developers can eliminate the possibility of having multiple versions of the same data in the database, and therefore improving the integrity of the data by reducing the possibility that one version of the data is incorrect. And then fourth, Another benefit of breaking up the data into smaller tables, related tables of data, is that you could rely on the software that managed the interaction between the data to protect it from deletions. When deleting a record that might break an important relationship that it might have had with other data. So you ensure data integrity by disallowing any potential harmful deletes of data within the database. And then also, and most importantly, by splitting up data into smaller chunks, you could retrieve data much more quickly than in the past. Okay, so let's speak in very practical terms. Imagine the scenario again. You want to create a database that contains customer order information. Now, in years past, you might just create a file, and each row of that file contains both the customer and the order information, just all in one long string. In addition to the other downsides that we outlined just a few moments ago using a text file or an Excel spreadsheet, there are other issues related to the data itself. For example, if each row contains both the customer and the order information, then there is the possibility that you have redundant information when you have a customer that orders twice. And what happens if the customer called himself Bob on the first order and Robert on the second order? Well, then it's going to look like there might be two different people, but ultimately, in reality, they were the same person. Or a better example might be if that customer moved from one year when he placed an order to the next year when he placed a second order. It would be difficult to determine that both orders were, in fact, ordered by the same customer. So it makes sense to split up that information into two separate but related structures, again called tables, within a relational database in order to manage this information. And so how do you go about splitting up the fields of information into one table or another? Again, you go through that process of normalization that I mentioned earlier. We'll talk about that again later. Okay. All right, so these are the types of problems that relational databases solved. Issues with data integrity and the size of the data. And there were other tangential benefits that were discovered along the way. But hopefully we've made a case, at least basically, made a case for the benefits of using relational databases. Let's now dig deeper into the actual objects that comprise a relational database. And so we start with the concept of a table, which is one of the foundational database objects. A table consists of columns and rows, or rather records, as you can see in the diagram of a customer table. And so you might be thinking to yourself, well, that looks a lot like, or at least reminds me of, an Excel spreadsheet. And to some degree that might be correct. A single column and a single row is often referred to as a field of data. The columns define the type of data that will be stored in the table. And the rows or the records are the actual data. So we might have a simple customer table, as you can see here, with the following columns: first name, last name, address, city, state, zip code, credit limit, and a customer since field to determine when they first ordered. And there might be some other fields of information or columns of information that we left out that might belong here as well based on what we're trying to accomplish with our database, but I think you get the idea. In order to maintain data integrity, we need to define a little bit more information about each of the columns, such as the type of data that we're going to save in that given row of data associated with that column. And in some cases, for example, like string data, we're going to have to not only define the fact that it's a character or string value, but also define the maximum number of characters that we should allow within that string or those characters. Okay, we'll need to define whether or not a particular record can be saved if it contains fields of information with no data, or rather if the field should contain null values, like we talked about a couple days ago. Okay, so to revisit an idea that I brought up just a moment ago, what is data integrity? Well, maintaining data integrity takes several forms, and it's one of the most important jobs of a relational database system. One simple example of data integrity is enforcing data types. So, for example, we may not want to allow somebody to add data to our database that sets the credit limit field that should be like a numeric field. For example, credit limit might be 2,000, 2000. But somebody might within an application or the database itself, try to spell out the word 2000, TWOTHOUSAND. And so that's a good example. We wouldn't want to allow that, because then that field of information is no longer calculable. You can't compare it. It's string textual information. The semantics aren't quite right. What we want is a numeric value that represents currency. So we'll probably use a money or small money field within SQL Server as the data type. And that will exclude the possibility that somebody will spell out $2,000, TWOTHO, you get the idea. It'll exclude that possibility because they're not going to be able to add those words to a currency value or a value of the database that only accepts currency values or money or small money fields. Okay. Now the same thing is true for dates, like the customer since column. We can see that we have that column defined as a date data type, and so it should only allow date and time values. And another example is the field state or province. It should only allow just a handful of characters if it's in the United States, just TX for Texas and CA for California and so on. So moving on, again, keeping in mind that we're talking about a customer database. As a rule, we may want to allow a record to be saved to the database that if the record does not include an address, we're okay. We can accept null values for address. Perhaps we didn't collect that information at a given conference where we were trying to collect potential user information. However, we might want to enforce a rule that does not allow a record to be saved to the database if the value for the first name or last name is null. After all, what customer or potential customer doesn't have a first or last name? And we kind of need that information in order that we can contact them somehow in the future. So to enforce these rules, as developers, we would define fields like address, city, state, zip to be nullable fields. These fields do not have to be supplied. The data does not have to be supplied in order for a record of data to be successfully saved into the database. However, if first name or last name is missing, the database can reject that attempt in order to maintain the integrity of the data. So to recap, to answer the question, what is data integrity? Simply put, data integrity is an attempt to make sure that all of the data in the database is correct and meaningful and useful for the purpose of any application that might need to use that data. Okay, coming back to that diagram from just a second ago, I passed over the column that was listed in the diagram called Customer ID, but it has a very important purpose. It's used to uniquely identify a given row of data. And since we're going to be using that field for that purpose, we'll define that field as what's called a primary key. Why do we need a primary key? What is a primary key? Well, primary key is a way to differentiate two customers, or rather two records that have the same name, for example. Just an example. So while you may have two records with the exact same information, they have the same name, perhaps even the same address, and so on, they're actually two different people logically in the world, or physically in the world. One field of data should be used to differentiate rows. And we're going to use this field to link this row of information with related information in other databases, and we'll see that in just a moment. One last thing about this field, no two rows can have the same value in a field that's defined as a primary key. Again, it must uniquely identify a given row of data. And so we can set a special property of that column called identity, which will automatically number each record of the data in that column as it's added to the database. And we're going to use that automatically numbered field of information for each record of data as its primary key as what differentiates this record from the other records within the table. And I'll show you how that's done a little bit later. Alright, so in addition to our customer table, we may want to define a second structure, a second table to store our orders. So we're going to call that an order table, as you can see here in our diagram. So you can see here that I have defined four columns: order ID, order date, order amount, and payment type. Now again, I probably left out some important information. So for our purposes, we're just going to investigate how this all works, but in a more real-life scenario, we might need to include some more information here. Most importantly, though, we left out the information that allows us to determine who actually created this order. Now, that's a real problem that we're going to have to address right now. We need to relate a row in the orders table back to a row within our customer table. And the way that we're going to do this is through the use of a foreign key. So we had primary keys before, and now we're going to use a foreign key. And so we're going to add one more column of information and call it customer ID. Now, it's not necessary to name the primary key and the foreign key the same thing. I just did that because I like to keep my sanity, okay? But sure, we could have named it anything that we wanted to name it. Now, by creating an order record and including a customer ID, we can easily tie back the order to any customer that to the customer that actually created the order. Also, we can easily tie back the order, all the orders that were ever created by this customer, and tally how much that customer has spent within our company through the last year or all time, and we can do a lot more with it because of that relationship. Okay, so just to recap, we have a primary key in the customer table that's called customer ID, and we have another key in another column in the order table that we called a foreign key. And so now it's possible to relate those two tables together. The primary key and the foreign key can be related together, thus making a relationship between these two tables. But from a database perspective, we still have a problem. If we were to delete a customer in the customer table, all of the associated orders that were placed by that customer would be what's called orphaned, which means that they would never be able to tell who ordered these items. So that would be a huge problem. So this is again where some of the rules that are enforced within a relational database management system come into play. What we need to do is create another special object in the database called a constraint. Specifically, what we need is a foreign key constraint between the order table and the customer table. So it's important to remember that just because you created a primary and foreign key in two different tables doesn't mean that they really have a relationship. You have to actually create a foreign key constraint between the two tables. And so the benefit is that whenever we define this relationship formally through a constraint using SQL Server, it'll be impossible to delete a customer record before deleting all his related orders first. The database just won't allow it. It'll throw an error. It'll scream. Because doing so would violate the integrity of the data in the database. You cannot have orphaned rows, especially if you take that approach. Alright, so that was a whirlwind overview, and I hope you can see at least some of the concepts of what a relational database is, why you would use it, the major objects and how they're related together. We talked about columns and rows and fields and tables and constraints and keys and things of that nature. And we're going to expand on those ideas throughout the coming videos. So if it didn't make sense in this video or you missed something, don't worry, we're going to cover it ad nauseum throughout the next couple of videos. But in a nutshell, relational databases help keep data structured and therefore easily managed. Relational databases reduce redundant data by splitting up potentially duplicate data into multiple tables, and it helps maintain the integrity of the data, among other things. Okay, so with some of those introductory concepts in mind, we're going to move on to explain a little bit more about databases in the next videos. All right, we'll see you there. Thank you.